this section, Professor Frank Smith. Please. Yes, I ask you before this workshop to take care about everything today. Please. Even about your own presentation. Sorry.
Ask some good questions of myself. I'll tell you. Our first presentation today is by Ian Roberts of Aerotech and Icing requirements and challenges for the aerospace community. Please go ahead, Ian.
Okay, so good morning, everyone. So this presentation is possibly a bit different to the other presentations you've seen. Obviously, the focus is on sea ice for this, but we're talking about aerospace issues now. And the idea is to give a broad overview of the icing requirements for the aerospace community and the challenges that we're facing, and maybe we could see if there are any synergies between the different communities, and we're always open to participating in other research where we can maybe bring together our knowledge. Because the background's sea ice, I thought I'd give a bit of background into Inflight icing, the origins of it, a bit about icing metrology, the new icing safety standards, which are bringing new challenges, as well as emissions efficiency and accuracy of predictions, which are also raising new challenges for both tunnel testing and for developing new systems, and then just a short summary. So in-flight icing goes right back to just after the Wright brothers flew. So the first papers related to icing were back in the 1920s, 1921, so just 18 years after the Wright brothers flew. And when they started really looking at ice formations. Of course, back then it was safety standards weren't the same, so they took up a biplane and just flew it through the icing conditions, and then somebody did some sketches to show what the ice looked like as they were flying through the air. So really, this was in the late 1920s, so there was a good appreciation. You can see from the pictures that we're starting to see on the right-hand side the rime ice, the hard ice that freezes instantaneously, whereas we've got the glaze ice on the left-hand side, which tends to form these horn formations. So this expanded quite rapidly. So by 1930s, they were already doing icing wind tunnel testing, and they appreciated that you can't just pour water in there, and they devised these nozzles which creates the droplet sprays that are required to recreate the atmospheric conditions. And these NACA nozzles are still very much in use today. Slight variations on them, but they're still being used in today's systems. So they acknowledged the issues with flight and icing, and quickly moved on to how do they prevent it. And so you can see on the left-hand side, there's these rubber inflatable boots, so they would inflate it to crack the ice. And those are still in use on aircraft such as regional turboprops. And then on the right-hand side, you can see a hot air system with a boiler at the bottom and steam pipes coming along to heat the leading edge. And it's very similar to what's used on all commercial aircraft, where hot air is taken out of the engine and run along the leading edges of the wings, where they have these called piccolo tubes, which are metal tubes with holes that are directed towards the leading edge to heat the leading edge. As they went into the 1940s, they were trying to increasingly understand the icing phenomena in terms of where it accretes on the aircraft and the atmospheric conditions, but also as more modern systems, such as on the right-hand side, you can see the pitot tube. They were understanding about ice formations inside those and trying to address the issues. As I say, this is just a quick run through of the early work. And so they started to appreciate the issues associated with droplets of different sizes. So they flew these aircraft with different size cylinders because the droplets have a mass inertia, and the bigger the body, the more inertially separation it gives. So by using these different size cylinders, they could get an indication of both the severity of the icing and the sizes of the droplets within those spectra. And so this is just a quick illustration, sort of in the bottom right-hand corner, you can see the line labeled number 1. A large droplet is almost, very large droplets are almost ballistic, whereas the small droplets would tend to follow the streamlines around the aircraft and maybe not impinge. As I mentioned earlier, during these early phases, a lot of the systems that are still in use today were invented. So we're talking back in the 1940s. So icing inhibiting fluids. So if you've been on an aircraft in Canada or somewhere like that, you know the ground de-icing systems that you might have seen. And some aircraft have these sort of weeping wings where icing fluid comes out from inside them, which has an anti-icing effect. Hot air systems on commercial airlines, electrothermal ice protection systems, which is an area that we sort of specialize in, is common on many rotating components, so on helicopters, propellers, and things like that. The pneumatic boots I mentioned earlier on regional aircraft, and then component ice prevention, so looking at pitot tubes, adding extra heaters there, and carburetor ice prevention, things like that. As I say, this is going very quickly through the background. So from the 1940s, 50s onwards, then it was basically, there was a lot of development in terms of testing and latterly simulations. So when computing power became available, so testing was looking at better characterization, improved uniformity within the icing test facilities, started using pressurized tunnels to simulate altitude, and then getting increasingly larger facilities for engine tests and things like that. Simulation, sort of in the 60s, 70s, computer simulation started to appear initially with 2D simulations for unprotected ice shapes, looking at characterizing heat transfer and things like that. But then these sort of gradually developed. So now 3D simulation is quite commonly used, mainly for analysis. For design work, 2D is often still used because it's still so much faster. So on the icing metrology, so there's the airworthiness standards, and Appendix C is the key part for the icing community, which defines the atmosphere that you've got to clear for. So this is in the FAA regulations, but there's common rules for EASA in Europe, and I guess it's now CAA in Europe have adopted the same rules. And really all these rules are still based on the data that was gathered in the late 1940s, early 1950s, and then really just on 3 papers that were produced. Those in turn drew on previous work, but it's, in some ways it's quite scary to read that there's a list of further work that needs to be done, but the standards are still based on these standards. So in terms of where icing occurs in the atmosphere, and its severity. We've got two basic classes which are called continuous maximum icing conditions, and these tend to be associated with stratiform clouds. So these are quite large, sort of longitudinally, so you can spend a long time in these atmospheres. So standard certifications is if you're holding in a holding pattern before landing, you could have 45 minutes in these conditions. The intermittent maximum conditions are cumuliform clouds, and those tend to be much severe, but they tend to be very short duration, so you might only be in there 2 or 3 minutes. So these are the figures that are in the airworthiness standards. So you can, it shows the altitudes which we're concerned with, so up to 22,000 feet, temperatures from 0 to minus 22 Fahrenheit. And that's for the continuous maximum. Whereas for the, there's a slightly different set of requirements for the intermittent maximum conditions, which can go to a slightly higher altitude, but tend to form at slightly colder conditions overall. They also, from the cylinder experiments that were shown earlier, it also gave an indication of the severity. So this is what we call the liquid water content, the grams per cubic meter. And there is a relationship both with temperature and the mean effective droplet diameter. So here we can see at near 0 degrees C, we can have very high LWC for small droplets, which decrease significantly as you go to the larger droplet end. But as you come down this curve here, we're getting colder and colder, and what's happening is that more and more of those small droplets, they freeze out more quickly, so a higher percentage have actually turned to ice crystals, because we're talking about supercooled liquid water here, so it's still water in the atmosphere, it hasn't nucleated yet. And similarly, these are the intermittent maximum conditions. So we were looking at 0.8 previously down here, whereas up here we're getting up towards 3 grams per cubic meter, so significantly more severe. As I mentioned earlier, these droplet sizes, severity and distributions were from a mixture of rotating cylinders, so that was the different diameters tell you what droplet sizes are in your spectrum, whereas the fixed cylinder, sorry, not sphere, the cylinders, that will tell you the largest droplet size in your spectrum, because it will say how far around the cylinder it accretes, gives you an indication of the largest droplets which are present in the atmosphere. And you probably know all about this thing is, if we're talking at the warmer conditions, we're forming the glaze ice that's shown in the right-hand picture, whereas if it's at the colder conditions, we're more towards the rime ice at the left-hand side. But for aircraft, it's quite complicated because it's a combination of the icing severity, the temperature, and the speed of the aircraft. For instance, if you're in a fast jet, they don't need ice protection systems because they just go faster. It takes the total air temperature above 0, so the ice doesn't form. Okay, so on to new icing standards. This is where there's new work happening in the field. When we say new, it's in icing terms, so it's actually from 1990s onwards. And really over the past few decades, there's 2 areas of research, which are supercooled large droplets and ice crystals or mixed phase icing conditions. So the supercooled large droplets, they've actually been known about and are in the DEFSTAN, which is the UK military standards, for quite a while, but they weren't incorporated into the civil certification standards. But in 1994, there was an American Eagle Flight 4184, which crashed in Roselawn. This was one of the ATR type aircraft, so it's a turboprop aircraft. So it had these inflatable boots as shown in the picture. And they designed it to these Appendix C conditions that I briefly discussed earlier, which goes up to around 40 or 50 microns as a mean diameter. But these supercooled large droplets, they do occur in the atmosphere, and they're more ballistic, as shown in the bottom picture, in their trajectory. What was happened is that they designed the ice protection system for the smaller droplets, but what was happening was the droplets were actually coming and accreting behind the ice protection system. This caused the loss of control of the aircraft and ultimately the loss of the aircraft itself. It's also an issue for aircraft engines. So there's been a number of issues with engines where these large droplets have gone inside and sort of caused the engines to stop and restart. But these engine conditions are more associated with ice crystals, which I'll discuss later. So after this Roselawn, there was quite a lot of research done to look at SLD and where they might occur in the atmosphere. So to give you an illustration, the relative size, the green dot would represent the typical Appendix C icing. Then there were two other regimes that were developed, which was the freezing drizzle, represented by the red spot, and then the freezing rain, which is the much larger droplet. So on the left-hand side here these are really two boundaries between which the icing conditions occur. So there's a freezing drizzle with an MVD of less than 40. So this is very much, it's mainly small droplets, but with a few that go on at a higher droplet sizes. And this is freezing drizzle with an MVD greater than 40 microns. So there's a higher percentage that are above the spectrum that's typically used for Appendix C. And then we get to freezing rain, and this extends this much further. So we're looking beyond 500 microns up to 1 millimeter, 2 millimeters of diameter. So we're talking significantly larger droplets. So in terms of the challenges, in terms of from an aerospace engineer point of view, trying to clear these aircraft. So the Icing wind tunnel testing. So the picture here shows a spray bar system within an Icing wind tunnel. So using the similar spray nozzles to was shown earlier. Because of the size of these droplets, what happens is you can end up with the droplets effectively falling out of the airstream, and they'll just be landing on the floor of the tunnel before they even reach the test section. Honora in France has just had built a vertical wind tunnel, so all the droplets are coming from above now to address those conditions. And there's a supercooling aspect. So if you've got large droplets which are close to 0 degrees C, it takes them a lot longer to cool down to the ambient conditions. So the water's being injected in at about 20 degrees C. So it takes time to cool down. The small droplets cool down very quickly in 0.5 meter to 1 meter, whereas these can take significantly longer. So you need a longer section before it reaches the test specimen. But as I go back to the first point, if you have a longer section, they drop out of the tunnel. airstream and land on the floor. We also need this, if I go back, this is a bimodal distribution that we're getting. So it's so typically for Appendix C, we'd be looking at a Langmuir D distribution, so a simple normal type distribution. Whereas this, we need a bimodal distribution, so a single nozzle won't produce that. So what they have to do is alternate the nozzles with different settings for each one to try and replicate these conditions. Of course, it takes a lot of variations of water pressure, air pressure to try and get it as close as possible. There's also droplet breakup. These are very large droplets. So as it goes through the contraction in the Icing wind tunnel, which are typically around 20:1, it can actually shear the droplets and break them up. So what has resulted is that quite often the icing cloud that you get is much smaller than your test section. So you only get a small area in the middle that you can use for testing. But also people are looking at having more gentle contractions. So as I said, going back to the Honora tunnel, where they've put a vertical tunnel in, they've got a very long contraction, but then you get aerodynamic issues associated with that. You get very large boundary layers on the wind tunnel walls. And also measurement, the accurate measurement of the droplets, which may splash or bounce, which I'll come on to in this slide, which is on the simulation side of things. So where you've got droplets impinging on the aircraft on the sort of leading edge near the stagnation point, these droplets splash similar to as shown in the top figure there. So all the water in the droplet isn't deposited on the wing. And similarly, if you've got a very oblique angle, they may skim off, sort of like stone skimming, and again, all the water isn't deposited. So there are, if you look in the bottom right figure, there are methods that have been implemented. So the black line shows the experiment, and if you were to run the codes normally, you would get the sort of upper red and green lines, but we have got corrections based on Weber number and the I can't remember how it's pronounced, Honsorge number, and the angle of the droplets, which gives good correlation. And these are our results. So we say, look how good it is, but you go to a different aerofoil and it doesn't work. So it's still an area of research. Is there a way which we can always get good correlation between experiment and test? As shown in the top picture as well, we've got re-emission of smaller droplets, which can accrete further downstream. It's very much a secondary issue. I don't think there's any significant issues associated with it at the moment that people know of, but it's something that people would like to try and understand, is where does all this splashed water go? And also, as I mentioned, for the Icing wind tunnel testing, there's also droplet breakup, which is where we can get large shear flows inside engines, etc., which may break up the droplets themselves. On the detection and protection side, the figure in the top right shows the ice on the front of an aircraft. Typically, in Appendix C, you would have got ice very close to the nose of the aircraft only. This bit of ice is shed, but this appears much further aft. So the current approach for most aircraft is visual cues. So if you start getting ice on your spinner or your side windscreen, you know you're in large droplet icing. Obviously, this isn't ideal, relying on the pilot noticing that there's water forming in different locations. So there is a big amount of research looking at ice sensors, for instance, the Sense for Ice program there. So on ice crystal icing, this was related to the Air France flight 447 that crashed going from Rio to Brazil. And that killed a significant number of people. And it was a series of events that caused it. But one of the main issues was the pitot tube became blocked with ice. Even though it was heated, these ice crystals went in, they formed on it, and the pilots lost lots of their instrumentation, which caused them to ultimately lose the aircraft. But also the ice crystals is a particular issue for engines. So there have been a number of issues where engines have had stall, flame out, or irreparable damage. If I can quickly switch to this. It's just a very quick view inside an engine. So you can see this very sort of wet, slushy ice formations form, and then they ultimately start to shed into the engine, which of course isn't ideal. So you can see some of these grow very large, and as you might understand, they can cause the compressors to stall, the combustors to flame out, etc. Most of these are recoverable, but there have been some instances where these have grown very large like this, where they've caused irreparable damage to the engines. So yes, it's quite a large issue. So obviously after this issue, especially as it was on a large commercial aircraft, there was a lot of research done. And so they found out that all these incidents occur at over 33,000 feet. So previously with supercooled liquid conditions, those only went up to 22,000 feet, maybe 26,000 feet for high liquid water content conditions. And they're associated with large mesoscale convective systems. So basically lots of thunderstorms have come together to produce a large continuous cloud that can be up to 100 kilometers across. These tend to occur in the tropics regions. And what you're getting is the warm air being brought up from the ground level, being thrown up into the high atmosphere where all these crystals are forming. And these may occur as just ice crystals or a mixed phase with both liquid water and ice crystals. I'll quickly go through some of this. So the engines associated issues, what we're getting is the crystals are going in, the engine surfaces are warm, they're melting it. The energy absorbed by the engine surfaces through the latent heat of fusion causes the temperature of that surface to drop below freezing, in which case the ice can then form. But as more ice forms, it creates a blanket over the engine, which then warms up, and then these ice accretions shed. So one of the main facilities is the NRC RATFAC, which is in Ottawa in Canada, where they've got a good system of producing ice crystals, and they've got in this part of the test chamber a water spray mist, and then they've got a simple contraction here where they can test parts of engines. This is still small scale, but very useful for testing parts of the engine, because it can also be pressurized to altitude conditions. So some of the challenges is realistic ice crystals. So most facilities have got a big block of ice that they grind up, and by controlling the feed rate and the spacing of the blades, they can get different ice crystals, but they're not atmospheric ice crystals. TU Braunschweig in Germany have actually got a chamber where they naturally grow crystals, but the issue is that they've probably got 2 or 3 seconds of running time before the ice crystals run out. And also the issue with larger scale testing is how can we achieve that? From the simulation side, it's quite an interesting problem. So it's quite a complex issue that you get ice crystals of different shapes, orientations. Some might be long cylinders, others might look more like dumbbells, where they impinge on the aircraft. And also these are quite hard. So they start, when you get ice forming, they then start eroding the ice formations that have occurred away. So it's quite a complex issue. And the crystal, so that's on the surface itself. The crystal simulations, these are non-spherical, as I said before, so they can go to different locations. And as they go into the engines or different components, they do start to melt. So you can get water forming around the outside of the crystal. And then, of course, the issue of shedding is how do we accurately predict when these blocks of ice are going to shed? There's also issues related to detection. You don't get ice crystals on wings because the wings are cold and the crystals just bounce off because there's nothing to have heated them by that point. So there's a range of sensors. So this one's got a sort of concave sensor that's heated so it can melt the crystals as they come in so they don't bounce back out again. But also looking at ground-based radar and flight-based radar sensors. Most of these issues have been overcome. So pitot tubes, they start using more power within them, and engine issues are largely overcome by redesigning, but they are some of the larger aircraft. So the 747-8, the latest version of the 747, they have to take large rerouting if there is icing crystals predicted. We're almost there. So that was looking at certification. There's also new challenges with new aircraft. So there's an increasing number of drones and things like these air taxis. They want to fly safe, but they've got a very low power budget. So a typical commercial or even a business jet might require several hundred kilowatts of power for de-icing and de-icing, whereas these may have 2 kilowatts of power available. So it's a significant challenge. Also, there's the global warming that we've heard about. So there's this push towards more electric aircraft, which are more efficient. They don't want to take the bleed air off the engine for these hot air de-icing systems that I said are in the leading edge of aircraft. So they want to use electrical sources instead. And you may say we could go to these de-icing boots, which are still very low power, but they cause issues with drag. And the new area is hydrogen fuel cells. So you might think that's perfect, it just produces water, but they produce contrails, and anecdotally, and it's this area of big research, is saying that that might be up to 60% of the pollution caused by the even standard aircraft is actually the contrails. They're reflecting the light back towards Earth, and therefore they're contributing to the global warming effect. So there are new systems. So instead of keeping the wing free of ice, we're looking at de-icing, so let ice form and then shed it, whether that's a thermal system or a mechanical system. Looking at icephobic materials, which I think Manish will talk about later, and other technologies such as microwaves and carbon nanotube heaters. I think I'm rapidly running out of time. So de-icing and low adhesion is an obvious way to reduce the power, but it does affect the performance of the aircraft. because you're letting ice grow, so therefore it's causing more drag. The expulsive systems are really noisy, so you don't really want those next to your passengers, because I think it would terrify them, quite honestly. I've been in a tunnel with them, and they're very, very noisy. Icephobic materials are the perfect solution. You don't get ice because it sheds it, but these have got to be robust to environmental conditions. So I might just skip over this slide. It's basically looking at how we're going to optimize these systems going forward. You can use, this work needs to be done to better understand ice adhesion and cohesion. Can we better combine technologies to be able to give de-icing effects? A bit on 3D ice accretions. The simple 3D ice accretion is where the droplets go around an aircraft, but also there's issues to do with swept components. So the picture in the right-hand side is a swept wing, and you get this sort of lobster tail ice. And there's some very interesting work on morphogenetic codes that are showing really good promise in terms of being able to recreate these ice formations. And it's basically coming down to a probabilistic method, both in terms of the freezing and releasing random particles of water into the stream. So I'll probably leave it at that. That was the last slide. Sorry, it's been a very quick run through, and there's no mathematics in it, I'm afraid. But it's sort of to trigger some discussion on how we may work together going forward.
Well, thank you, Ian. Thank you. Very, very interesting talk. This is Frank here. You know me.
Yeah.
Are there any questions in the room, particularly? Yeah, Sasha.
I have two questions. First, it's is the erosion due to droplet impact is still a problem for industry? This first question. And second, in your experiments and in other analysis you did, is the I understand only freshwater droplets were used. Did you try salted water or water with something else, changing the droplets? Like droplets with salted water, it's a big problem for icing of offshore structures. It's different from aircraft icing, but I believe it's quite similar. Thank you.
Okay, so in terms of the erosion, so we get the issues for the ice crystals, the formations that appear, you end up with quite pointy ice accretions because the crystals are actually eroding. So some of the crystals is forming the ice formation, but they're also getting eroded away, these ice formations, by the crystals themselves. So they're changing the way in which the ice forms, but also on the erosion for the what we're looking at in terms of icephobic coatings is a particular issue. So far in my experience, I've never seen a coating that's lasted possibly more than 10 minutes. Because after 10 minutes, they've all been eroded away. So I know Manish will talk about this later, but it's a significant issue with the robustness. And on the salt water, no, it's not something that we typically look at. It is part of the clearance requirements for aircraft, but that's more for them based on the ground and being robust to corrosion, things like that.
Okay, thank you. I'm just wondering, Ian, are there any particular features of your talk and your work or experience where that you think might carry over to sea ice modeling?
I think there's work on the, so we're looking at the moment at these mechanical systems. So if I show the pretty picture of the ice being shed, so this is fundamental properties of the ice, getting good values for adhesion and cohesion. So we did a whole lot of testing at NRC in Canada. I spent 5 weeks out there. We had a spin rig that we accreted ice and it shed it. But I feel that there's some stochastics needed in there, because we could test the same specimen in the same conditions and the adhesive property would vary by maybe up to 200, 300%. And I guess it's this fundamental properties of ice, which is something that we're particularly interested in, because if we're going to go low power, we need to understand this better.
Okay, thank you. Any more? No, okay, well, thank you again, Ian, for your very interesting talk. And good, we'll clap again.
Okay,